at the University of Provence and at the Paris Observatory. And she's now here with this clinical guest program in Stockholm with us, and she's staying here for until Friday still. She has been before at the Light Observatory with Davina Pudishoop, where she was in a Nova postdoctoral fellow, and before that she was at Berkeley, Nottingham, and made her PhD in Cambridge. So, welcome.
Thank you very much.
Thanks for the lecture.
Okay, so you guys get me for the first time. This is my first of 2 talks today. I'm also sitting in the physics department after lunch. Blatant advertising, but if anyone after I've talked about all of this wants to know more about the physics side of what I do, come and listen to my physics talk at 1:15 in FA 31 or 32 or something like this. And on Friday I'm actually giving an astronomy talk to the astronomy department in the morning. I have to earn my money from this I can't do Swedish. Just before or whatever. Yeah. My Dutch is okay, but my Swedish doesn't happen apart from Taxamika. Actually, I came to Sweden when I was 14, and I led this little song around the campfire, and I remember the first line goes, temperature. So there we go, that's the way I have a bit of Swedish I know. I don't have a clue what it means, but I remember the tune. So, I mean, it's very exciting, because I'd been to Stockholm when I was 14, and what shocks me is actually I hardly remembered any of it. I remembered going to see the big ship in the museum, which was there then. I remembered seeing the changing of the guard, and that was the only things I could remember of Stockholm. So I've had great fun, because I arrived at the weekend when it was still sunny, and I've seen your beautiful city in the sun and the heat and the warmth, so I have a very good impression of Stockholm. So anyway, my remit for this talk was to aim it mostly at the graduate students, so I'm talking to this corner of the room, but please don't feel free to stop me, and please stop me if you're not sure or you want to ask a question. If I don't get all the way to the end, it doesn't matter. I'd rather you could take something away with you. And my remit was to sort of talk to predominantly the more astrobiology people here in Stockholm about astrochemistry and how we're using that in an astrobiology sense. So hopefully that's what I'm going to do today. And maybe I'm not working. Right. Okay, well the lace is working even if this isn't working. So this is an image of the Ophiuchus clouds, which was taken with the Spitzer IRAC, and thank you very much. And as you can see, it's a very beautiful image of a star-forming region, and of course astronomy is all about beautiful images. This is what grabs the attention of the press and the media. And it's this kind of thing that grabs the attention, of course, of the general public, and really allows us to indulge in our life's ambition of doing something we really enjoy and we really love as astronomers, because it's a huge advantage compared to lots of other sciences. And I know, because I have one foot in chemistry and another foot in physics as well, and I am kind of three-legged when it comes to my interdisciplinary work, and selling the sort of astronomy aspects of what I do is a whole lot easier than selling the very pure science aspects, and so this is a very big advantage. But in reality, images like this, although they're very beautiful, are not the key thing that are really driving us in astronomy. We want to really know a lot of information behind this. We want to know about the physical conditions, temperatures, pressures. We want to know what the objects are. We want to understand how they're forming, how they're evolving, and how we really get from sort of really atoms that are forming in nucleosynthesis processes in stars all the way through to, assuming the philosophical questions are aside, that we can form complex beings such as life, such as ourselves that are sitting in this room here. And that's a pretty big step from a hydrogen atom undergoing nuclear fission all the way to a human being and its complexities. And we know that probably, well, I don't think it's on this site, I think it's down the road. There are a whole bunch of biologists probably studying all the physiology and all the chemical processes going on in our own bodies that control us as a very sort of intimate biological machine. So how do we really get from one place to the other? I think I need a new battery. And where does chemistry come in? Because really in astronomy it looks like it's pretty pictures and lots of interesting astronomical aspects, but really where does chemistry come in? Well, I want to come back and remind you something probably you maybe already know, but bear with me if you do, and bear with me if you don't. But sort of, if you like, the picture of star formation as we currently understand it, with lots of holes in it and lots of things we can throw away. Now, it doesn't really matter where we start in the star formation cycle. In fact, the universe is a great recycling project in many ways, because we have star formation just about still ongoing in our visible universe now, in terms of its age. And we had star and galaxy formation going on back in many epochs of time, and we'll be able to observe it, relatively speaking, in our lifetimes, all of our lifetimes. And so what we want to understand is we want to understand where that's happening. Now, here's an image of Barnard 68. It's a cold, dark molecular core. It's actually not forming a star. But it's a very good example of a dense molecular core, because if we look in the visible, what we see is what looks like a black hole on the sky. And that's not the kind of black hole that Stephen Hawking talks about, but that's really a collection of gas and dust in a cloud, which is obscuring the starlight that's behind it. It's scattering that light. So if we look carefully, sometimes at the edges we see reddened stars. If we look in the infrared, because the infrared light can penetrate the gas and the dust, we can actually see the objects behind, and maybe even, if there are any, within the cloud. But these are the kinds of objects we're interested in looking at, and here our Southern Hemisphere colleagues have great advantages over all of us, because they can tell, first of all the students in a class or something to go and look at the night sky. You guys here in Stockholm have the same problem I have in Glasgow. It's pretty difficult to see the night sky most of the time, not only due to light pollution, but also due to the fact it's cloudy. But if you look in the Southern Hemisphere, especially at the Milky Way, it's very easy to see dense molecular clouds. And for those of you who've ever observed in Chile, or had the opportunity to go to the Southern Hemisphere, it's really quite amazing when you see the Milky Way. It's even very different to know how it looks in the north of Sweden or the north of Scotland, where we don't have light pollution particularly. It's really amazing to see the Southern Hemisphere Milky Way. But these clouds of gas and dust, what they are really is they're both our stellar nurseries and our chemical cauldrons of the universe. So they are the place where new stars are going to be born and formed. So that also means that's the place where there's the dust available to form planets, and that means, by inference, potentially life. But it also happens to be the place where we find all the atoms are essentially aggregating together, sticking together in chemical bonding and forming molecules. This is really the place we find molecules in space as well. So molecules are intrinsically linked together with the star formation process. And that's not so very surprising, because these clouds of gas and dust are actually self-sustaining. Their gravitational force, which is trying to pull them in and collapse, is, when they're just sitting around like this in a sort of quiescent phase, really balanced by the gas pressure in the cloud. Now, as soon as you start forming bigger and bigger molecules, what you're doing, even think of going from a hydrogen atom to an H2 molecules. You've even then increased the density of states, the number of energy levels available through which you can dissipate energy. And because of that, you have an ability to cool the gas that you're looking at. And we know as astronomers that's a very common thing. Yeah, when people are looking at galactic formation, they're very interested in where the H2 is and where the H atoms are, because H2 is known as a very efficient cooling gas. On the other hand, if we start adding carbon atoms in and getting to bigger and bigger molecules, we've got many, many more degrees of freedom, many more ways the molecule could vibrate, rotate, okay? And consequently, we can dissipate more and more energy. And as we get to being able to dissipate more energy and cooling down the cloud, okay, it's a little bit like a closed system. There's not lots more atoms feeding into the cloud, so consequently, we've got less effective bodies banging against the sides of the wall, the sides of our closed system, the cloud. So therefore, the total pressure starts to go down, and consequently, gravitational collapse can overtake the gas pressure, which is sustaining the cloud, and some kind of collapse happens. Now, that's a bit of a simplistic view, because, of course, we now know that collapse occurs from the inside outwards in dense cores, which have got very dense and start burning, and it's a little bit more complicated, but that's the way we can link the physics and the chemistry together.
Excuse me, I think you said that H2 is an efficient coolant.
It can be, yes.
I thought because it was infrared inactive that it was not.
Well, it has still a lot. It's not an efficient coolant at getting down to 10 Kelvin or something like this. But if you want to go from 10 to the 8 Kelvin to 10 to the 4 Kelvin or something, then it's quite efficient. Okay. Yeah.
Then you may have even. I mean, then you don't have H2, of course, right?
Well,
or you mean H2 by the ionized or in molecular?
In ionized form, in molecular form.
Yeah.
So long as you've got more energy levels available, that's the point where you're starting to reduce the.
Yeah.
I'm not
The
an
people-
H2 expert, but I know that H2 is a useful, I mean, for example, with the universe itself, once we start forming hydrogen and then we start forming H2, the universe as a whole cools down. So that's already that's a huge different step, but it's a good example. The CO is a very good cooling gas because it's also self-shielding.
But the molecular H2 is less efficient than the cooling that we have in all regular stars now, of course.
Yes. And H2 is not the key coolant in these clouds, for example. CO is.
CO, yeah. Right. And down to 10 Kelvin, what is that still CO?
Yeah, what happens with CO? CO is quite an interesting issue, actually. CO is formed really right at the edges of the cloud in the gas phase from reaction between C plus and oxygen.
Uh-huh.
We assume, well, that's what we seem to see. And when you form CO, it has a triple bond. And this triple bond is basically stable to the pervading interstellar radiation field. There's not enough energy in the interstellar radiation field to break that triple bond.
Mm-hmm.
So what happens to the CO is it essentially becomes self-shielding. It essentially starts, inside these clouds, very little UV light is really penetrating. The UV light, the UV field inside the cloud is generated by cosmic rays hitting H2, exciting its really excited state, and that dropping back down again. That's where UV photons come from, inside the cloud. So the CO becomes very efficient at shielding the cloud from all the energetic processes that could be potentially warming it up and putting energy back into it. So CO becomes an effective coolant, not just because it has energy levels available,
Shielded.
but also because it's shielding. So,
Interesting.
yeah. Okay, so when we get to these clouds, okay, this is part of the Eagle Nebula. I'm taking the liberty of taking different parts of the sky here. But basically, within these dense clouds, and we don't quite know really how the clouds form, but within these dense clouds, for reasons also we don't fully understand, the cloud is not nice and smooth, but it's clumpy. And I guess the best way to describe this, I usually use Glasgow Airport, but I guess I can use Stockholm Airport. When you fly in an airplane into Stockholm Airport and it's a cloudy day, when we look from here and we look up at the sky, it looks pretty uniformly cloudy. Pretty much we could guarantee if we were in an aeroplane looking down, there'd be places we could see the ground, places we couldn't. As we were flying through the clouds, there'd be a greater or lesser sort of field of view that we could have, depending on the density, if you like, of the water vapor and how intense the cloud cover is. And it's the same thing in these clouds here. Essentially, we have clumpiness. We have different regions of different density across the cloud. And so some of these regions eventually start collapsing under their own gravitational force, and this is an image from Orion. And basically what we can see if we look in the infrared is we can see also sort of dusty features in the visible and near infrared, and sometimes we can see bright objects at the centre, which are essentially protostellar objects. So what we have is we have a collapsing cloud that's really collapsing from the inside out. But at the centre we have what we call a protostellar star. It's, if you like, a baby star that's neither a teenager nor a grown-up. It's certainly not on the HR diagram yet. It's not a main sequence star. And around it, due to conservation of angular momentum, we've got a disk of gas and dust. And it's from this disk of gas and dust that really our planets are going to form. And there's a whole science involved in trying to understand planet formation, and the only thing I can say is right now, despite all the advances we've made and all the planets we've found, we still can't build a single model that can rebuild our own solar system. We certainly can't build 9 planets in the right place, of the right type, at the right time. We find it pretty hard to do 2, and certainly 3 is more and more difficult, and we can't always get the gas giants and the rocky planets in the right place, so there's lots we don't understand still about planet formation. Worse than that, we still don't quite fully understand how this collapse really happens. We have very good models, but we don't really understand. And worse than that, we don't really understand how these clouds form in the first place, because eventually when we have a solar system like our own, eventually the star that's really at the centre of the solar system, or potentially the binary system, because many more stars that form as binaries than single stars, but eventually they die, and when they die it can be a supernova explosion or a sort of quiet, controlled red giant phase, and then a silent death, if you like, of the star. But whatever happens, all the material that was in the solar system essentially is thrown back into space in atomic or very basic molecular form, and off it goes all over again, and it basically refuels the interstellar medium, and at some point in time collates together and forms a cloud of gas and dust, which is going to start again the interstellar process. Now, of course, there is one change that happens every time we go through this cycle, and that is in the star death process we start to increase metallicity, or what astronomers call metallicity. I find this very confusing. I'll come to this in a moment, but chemists and physicists work with the periodic table and astronomers work with metallicity. So nonetheless, what we're getting is heavier and heavier elements as we go around this cycle. So that's also very interesting from a chemistry point of view or a biology point of view, because it gives us access to heavier elements, have more orbitals available, have more ways of bonding, have more ways we can put things together, have more ways in which we can attach things as ligands and do more interesting chemistry. So it's already very interesting for us if we can make heavier metals or heavier materials. So this is our kind of picture of star formation, if you like. And the key sort of areas that I really focus on are pre-stellar cores, these things here, collapsing cores, and young stellar objects. So these are these sort of baby stars and the bits before baby stars. And gradually I'm sort of moving into this phase here, but not so much. And so the kind of material I'm looking at most of the time, the interstellar medium, is 99% by mass gas, mostly hydrogen, H2 and helium, and 1% by mass dust, which is sort of mostly silicon and carbon, pardon me, with some metals, many metals, all metals really, but these are the most popular ones, and all the molecules. And so that's where we're really coming from. And down here is, of course, the link that comes to biology. And given that all the things that we want to do the biology with on the planet have to come from somewhere, the bottom line is they come back from the clouds here. Of course, if we went back further, they came back from the last solar system that exploded and died and mixed itself up again. And well, they came from the last planet that had life on it. You can keep going round and round in circles to argue where it came from. But nonetheless, we think there's some kind of link, maybe not a direct link, but there is certainly some kind of link between what's happening here and what ends up happening here. It doesn't mean to say the life is produced here and ends up here. Not at all. I don't want to claim that in any way. So please don't go away with that. So our key as astronomers is to use the electromagnetic spectrum. Okay? Really, as astronomers, we don't go very far. If we make it to Mars, or we make it to with Cassini-Huygens, or to Titan, or something like this, it's really like sort of going down the road in Stockholm. It's not going very far away at all. You haven't even made it to Gothenburg. You certainly haven't made it into Lapland. You certainly haven't really explored with your eyes and your body and yourself and felt and experienced the rest of the universe. The way we do that is by using the electromagnetic spectrum. And of course, if we look at the same part of the universe, now this is just because I happen to be able to find the images in all parts of the spectrum in the same kind of colours, but this is near M42. But if you look near M42 in different regions of the spectrum, I just think this is a nice way of showing that the picture we get of the universe looks completely different depending on which energy regime, or if you like, which wavelength regime we're looking in. And you probably know from experience that when you walk along that long corridor upstairs in the astronomy department from one end to the other, you're pretty much going from one end to the other of this scale, and different people are using different parts of the spectrum to do their own little piece of astronomy. And actually what's really nice in the last sort of 5 or 10 years in astronomy, and one of the reasons it's becoming so much more interdisciplinary in astrobiology and astrochemistry, in my opinion, is that instead of calling yourself a radio astronomer or a gamma ray astronomer, we are all trying now to really look across the spectrum at many different areas. If you're working in star formation, for example, you can't ignore the fact that as soon as X-ray Chandra went up, we started seeing X-rays and XMM Newton, we started seeing X-rays strongly emitted from low-mass young stellar objects. That's a pretty important thing we have to take care of if there's chemistry going on, because there's a huge energy source that can be driving chemistry. On the other hand, you know, if you're looking at molecules, the radio wave is quite a, radio and microwave is quite a useful region of the spectrum, and that's sort of what I want to say now. From a molecular viewpoint, what's most important? Now, in actual fact, wherever you're looking in the electromagnetic spectrum, be it a general continuum observation or a 21 centimetre line of hydrogen or something, what we all do when we make an image in astronomy is we use some kind of spectroscopy. We use some kind of electromagnetic black body radiation, or we use a particular molecule. And all cosmologists, they spend hours and hours and hours imaging galaxies in H2 lines or hydrogen lines, or CO lines or whatever. They look at certain specific transitions, and they can use those specific transitions and work out the Z at which their galaxy is the redshift at which it happens to be moving away from us, simply because at some point in the dim and distant past, at the turn of the last century, not the most recent one, the one before, there were a bunch of people sitting in a lab working out what the gas phase spectra or the radio spectra or anything else with molecules like H2 and CO looked like. In fact, H2 was really done even before that in the 17th or 18th centuries, when people like Balmer and Paschen and Lyman and all the others started looking at line transitions in atoms and molecules and things. And those simple transitions, that simple stuff that you learn when you're an undergraduate physicist or chemist, or when you're first doing your astronomy courses, is really the stuff that we use as astronomers to observe the universe. It's just that we forget what we're looking at, because what we're more interested in is what the object looks like and what it's doing and everything else. And that's why processes like radiative transfer and everything else become important, because we have to think about what's happening to the transitions that we're using to probe the environments we're looking at, especially as astrochemists. And there are two areas which are really very important in doing molecular work, and that is molecular rotation and molecular vibration. Really, this region, the microwave and the infrared, that, to a chemist, is the ultimate area for identifying molecules. Up here we can see electronic transitions, change of valence electrons. We can see if a molecule has conjugation, double bonds or triple bonds in it, especially in organic molecules. But if we were to go to one of the stinky chemistry labs somewhere nearby and sniff very hard and see what kind of synthetic organic cookery was going on, one thing you'll find is that these regions of the spectrum would be the ultimate regions that people would go and put their little sample in when they've made their little white powder that they hope was a drug to cure cancer or something. And in order to look at its structure and check what it's doing, they'd be using a lot of spectroscopy. And that's exactly what we do in space. The only difference is we don't have a nice little sample that we carry around with us. We infer it from what we're seeing in a line of sight. Okay. And basically, we can see all sorts of different spectra. We can see solid spectra. We can see all sorts of different transitions. And all I've got here is a very simple picture of water. And this is actually solid water, because that happens to be a very useful material I look at a lot. But we have a bunch of transitions here. We have what's called the libration mode, which is while the water's sitting on its axis, sort of wobbling around its own axis. We have the bending mode, which is where the water's sort of sitting, wagging around like this. And we have the symmetric and asymmetric stretching modes down here, which is where the water is either oscillating like this or like this. Okay? I've done that before, strangely. When you put your microwave oven on and you want to heat something up, the great thing is that what you actually do is excite a rotational transition of water, and pretty much what your water molecule is doing then is spinning round and round like this. And the great thing is that's why you always need a turning plate in your microwave, because otherwise you set up standing waves and you have interference in your microwave, and that's why you get bits of your food that are really hot and bits of your food that are really cold. And the great thing is, I tell all my students, if you take, I don't know if anyone has tried this, but if you take the rotatable plate out of the microwave and you put in a bar of chocolate, we use Cadbury's Dairy Milk to demonstrate it, because it melts quite nicely and it's nice chocolate. And you'll roughly see that every 3 to 6 centimetres, depending on exactly what frequency your microwave is working at, provided it's not rotating, it will melt and then not melt and melt and then not melt, and it's really cool. You can actually do that. Don't put it on the highest power though for about 10 seconds, because you will melt everything. You can do that anyway. And what we have to remember in our head is everything we're looking at and everything we're doing is actually these molecules vibrating and rotating. That's really what we're using to probe what's going on in space. Okay, so how do we do that? Well, hopefully this is something that many of you already know, but nonetheless, if we want to look at molecular vibrations in the infrared, what we need something to look at them, and we need sort of a telescope or a satellite or a telescope hopefully flying on an aeroplane, which can go to quite high up in the atmosphere, so that we have a minimum amount of atmosphere to go through, and we want to be in a very dry place, because unfortunately we have an atmosphere that's full of things like CO2 and water, and the atmosphere is therefore not opaque, at infrared wavelengths in the regions where water and CO2 are, and consequently it's quite hard to see what's actually going on in space, because what we actually see is everything going on in the atmosphere. And for those of you who've ever sat at the top of Mauna Kea in Hawaii and thought that you found a really exciting absorption line like I did the other week, and then realised that you've seen the ozone layer, it still exists above Hawaii, that's good news, then always remember that of course there are molecules in the atmosphere. It's very exciting when you find something exciting in the atmosphere, and you can often see very exciting things, and it was very good. Against Saturn we found ozone, very nice. It was in absorption though, so we knew it was definitely the atmosphere. It's quite deep as well, so there's quite a lot of ozone above Mauna Kea at that point in time. So that's quite good. But anyway, how do we do this in space? Well, what we do is we take some kind of telescope, obviously, and we point it towards our molecular cloud, and we either look for a background star, or we look for an embedded object in the cloud, an infrared source. And against the infrared source, which gives us some kind of IR blackbody continuum, maybe not quite a simple blackbody, but nonetheless, we see absorption features. And those absorption features tell us about the material in the line of sight. And that's predominantly what's true for solid phase material. For gas phase material, we can see the lines in absorption or emission. And that might sound very confusing, but what we have to think about is we have to think about the fact that these clouds are not in thermodynamic equilibrium. Okay, we don't get a nice Maxwell-Boltzmann relation referring as to how the states have been populated. So what we have to think about is we have to think about how the radiative transfer occurs in this system. And one very good example of radiative transfer is if we want to understand our own atmosphere. If we don't take radiative transfer into account, it's very difficult to model the processes that are going on in our own atmosphere and to understand whether global warming is real or not, and why chemistry is going a certain way, and the same thing happens in space. Okay, so what about complex molecules? Well, there are lots of different tenuous detections, and here's a tenuous detection of molecules that are sort of hyped as being biologically relevant, okay? And now glycine is, if you like, one of the simplest amino acids, i.e. it has the right groups chemically at one end and the other to be considered an amino acid, because it has an acid group at one end and an NH2 group at the other end. And tenuously, if you go and search in the radio frequency, you can find a whole bunch of transitions which you can assign to this molecule. One of the problems is that there could be another whole bunch of transitions which we never see at all. And so some people would argue this is because molecules aren't in thermodynamic equilibrium, maybe some modes are suppressed in space, lab spectra don't look like space spectra. So this is a very uncertain and controversial detection from 2003. It hasn't been receded, but it hasn't necessarily been confirmed by anyone else since then either. But nonetheless, it gives us the opportunity, it opens up the prospect that we could have complex molecules in space. And let's be frank, there must be probably complex molecules in space, because we all agree that we have gas and dust. And so if you ask any chemist, right down from a 14-year-old up to, you know, the top professor who came last year and won the Nobel Prize in chemistry, well, how do you get from an atom all the way to a dust grain? They will probably tell you, well, the atom will join with some other atoms and form a molecule, and then those molecules will cluster together and form what the chemists call a cluster. Now it's trendily known as a nanoparticle, because obviously that gets you more money for your research. And then the nanoparticles will cluster together and form a dust grain. And if you continue with the planet building people, the dust grains aggregate together and form boulders, and then the boulders form rocks, and then the rocks form planetesimals, and so on, and then we get a planet. But nonetheless, what that means is that somewhere in the whole process of going from the atom to the kind of rocky planet, I hope, that we live on, at least for the first little bit, okay, we must have gone through all these different things that chemists are used to seeing, clusters, complexes where different molecules are joined together, and so on. And what that means is probably we have the potential in space to form many, many different things. The question is what we're sensitive to observing. And that can be kind of a little bit of a problem. And in actual fact, here is the spectrum of W33A. In fact, for many years it was always put up at conferences as this is what nice spectrum looks like in space. Actually, I'd like to highlight this thing. It's very atypical of star-forming regions. W33A is quite an exceptional, unusual object that we happen to point ISO at in the late 1990s and see a wonderful spectrum which forevermore has become the prerequisite of all the things we could find in space, whereas in reality it's a very complicated spectrum. But what we see here is a whole bunch of things, a whole bunch of chemicals, if you like, which if you were to take them to a chemist and say, if you had all these things available in some form, do you think you could form all the organic materials necessary for life? Well, pretty much probably yes, because you've got things containing carbon, oxygen, nitrogen, sulfur. The big thing that's missing actually here is a phosphorus-containing molecule. And sulfur and phosphorus chemistry are not very well known or understood in space at the moment. And that's a very important thing from an astrochemistry point of view, from the prebiotic phase, because we know the phosphorus is down here and the iron and everything else, and we have a source of iron. The iron can be in the dust with the silicates, or it could be in the iron sulfides, which now missions like Stardust are finding very effectively. But phosphorus is a little bit of a problem. We've hardly got any molecules detected with phosphorus in them. Sulfur is a bit of a problem. We don't understand the sulfur chemistry. Even the nitrogen chemistry is a bit of a pain in the butt, to be frank, because we don't really understand how that works either. So we're not doing very well, really. We're quite good at carbon chemistry, although we don't quite understand that, really. But nonetheless, we have molecules there which are nice precursors. In particular, well, we don't have any of it here, but just down here, there is a little feature which is sort of in here, which isn't labelled on this one, which is ammonia. And we now have sort of detected ammonia in this. I should maybe add that in. We also have CO2 and CO and water, which is very useful. We certainly have some aliphatic species and aromatic species here that we can't quite decipher. We have a bunch of features over here, this big thing here. Some people think it's NH4+, but that's pretty unlikely in my opinion, so I don't label it that way. In fact, probably this is also related to a lot of species on the grain surface. And here we have the silicate features that are related to how the grain itself is formed. So what we tend to do when we're discussing in astronomy and interstellar space and star formation is we define an ice. And an ice is any volatile gas condensing into solid form at less than 273 Kelvin. And the reason I define that is because otherwise silicates can become ices, and they're really not really ices at all. And what I kind of mean by these ices is really these things in red. Some of them form on the grain surface, and some of them are condensed onto the grain surface in space. But nonetheless, if we went in the lab and we had a surface at below 273 Kelvin, and we were to expose the surface to these materials, they would condense out onto the surface. In order to do that with silicate, we'd have to make a silicate gas first of all, and of course silicate isn't a gas in the first place at 273. It's really a refractory material, and how we define these things and the words we use they're a language problem, not a science problem, so just bear with me. But these ices are really solids. But if you're in physics, you call them condensed matter. If you're in chemistry, you call them solids, and if you're in astronomy, you call them ices. So here's my periodic table. Hopefully you've all seen this before, right? Not showing you anything new. Sometimes, I'm not sure, but anyway, periodic table. If I'm talking to PChem 101 or Chemistry for Physics 101, what I pretty much say is, okay, hydrogen and helium, and then here we have metals, here we have transition metals, and here we have non-metals, okay? That's a pretty good classification that you learn about. You spend hours studying when you're doing your high school and everything else, all the trends, what these things are doing. All the way up to here, uranium. Everything is naturally occurring. These things up here, no longer naturally occurring. They're the things we've made in the lab that are all radioactive. Down here, iron is a very stable material that comes through the nucleosynthesis process. Lots of interesting things going on. Okay, here is my astronomer's periodic table. As you see, I missed a load of the materials out, okay? Here's my definition. Hydrogen and helium are non-metals. They were formed just after the Big Bang. They're all left over from recombination era. Metals are everything else that are formed subsequently in fission processes. So suddenly when you become an astronomer, carbon, nitrogen, oxygen, neon, argon, sulfur, all these things become metals. And I must admit, when I first moved from being a chemist stroke physicist to being an astronomer, it did take me about 2 years of conferences to work out that this is what all of this meant. And actually, metallicity is a very important discussion in astrobiology, because one of the things we've discovered is, depending on the metallicity, the degree of these materials that we find in a star as it's forming, gives us the propensity, the likelihood of a star actually having planets around it or not. Depending how many planets around it and what kind of planet is directly related to metallicity. That was a very interesting published result just a few years ago. And so that's kind of quite interesting, isn't it? Because here we are on a planet with a huge abundance of metals, although the planets around us don't necessarily have that same thing. And there's a lot of speculation about why we are such an unusual environment. There's the chance, of course, that when our star and our protostellar disk was in its early stages, there was somehow a nearby supernova explosion that seeded our protostellar disk where the planets were forming with heavy elements, and therefore that's why we have a lot of heavy elements in our environment. Could be true, could not be true, we can't really tell, we don't know. But certainly we have rather unusual conditions on Earth. We think it's usual, but it's actually very unusual here on Earth compared to everywhere else. The other thing I want to point out is the sizes of my boxes on my astronomical periodic table. And that's because the boxes are made to represent the abundances, or if you like, the amounts of these atoms that exist in the whole universe, give or take an order of magnitude. Just bear with me. But as you can see, all the ones that aren't there, that's because they're so small that I don't have a pixel small enough on my screen, never mind on this screen, to actually illustrate that it exists. And as you can see with sulfur and argon, I also couldn't really draw the boxes. But nonetheless, here are the things, again, phosphorus is not on that list, but here are the things: iron, magnesium, calcium, which your bones are made of, doesn't appear on this list. Carbon, nitrogen, oxygen, sulfur, all the things that we're really interested in. Dead easy to put hydrogen with them all, but all the things we're interested in for organic chemistry, for the chemistry that's driving our bodies and doing our physiology every day, is occurring with these very uninteresting, unimportant parts of the universe, actually. Most of the universe is hydrogen and helium, and that's it. And so it's really amazing, actually, that we can form any molecules at all. I'm going to skip this bit. But nonetheless, we use molecules. So what I want to do is I want to show you how we actually use molecules in astrochemistry. What can we use it for? You don't have to read all the words. I want you to look mostly at the pretty pictures. But you can go back, and this comes from a Nature paper from 1998 from Vedasani and Langer. But it's a really nice illustration of outflows and dynamics. So when we have a protostellar object that's forming, we have this baby star at the centre, we have a ring of gas and dust. What we see in low mass objects is two huge jets coming out of the system at very high velocity, and we can actually track these jets, and by looking at whether the transitions from molecules in those jets are blue shifted or red shifted, very clever astronomers with much more observational capability than I could ever have can tell us about whether the outflow is flowing away from us or towards us. What about the dynamics? Is there any torsion in this jet? What are the interesting features around the star? Is it crashing into another cloud nearby and forming a HH object or anything else, a heavy carrier object? And lots of people will use a single transition, say something like a CO molecule. What we're looking at here is the rotational transition of 12CO from 2 to 1. Okay, there's something that way back when in maybe first or second year chemistry or physics you looked at, you learned about rotational levels, you learned about exciting the molecule up to a rotational level and letting it drop back down again. This is a very simple transition, just the CO molecule rotating, watching it drop back down, and according to how that shifted, velocity shifted from its real rest position when we're observing it across this field of view, we can tell something about the dynamics. So we're not interested really in what the CO molecule is doing per se, we're interested in all the hydrodynamics, all the turbulent flow, all the processing that's going on, the physical processing. So we use the molecule as a probe of outflow and dynamics. And what you see here is, what they illustrate is that this lobe of the outflow is actually blue shifted and this lobe is red shifted. And similarly, they show another example where actually there's an infall. I believe this is the C18O2 to 1 transition. This is of course in this direction, and with a different molecule they can look at how the material from the disk is falling into the star whilst other material is being ejected out from the star. So what else can we do? Well, the other thing we can do is we can try and understand how desorption processes happen. We can have a look at physical processes. We can use gas phase plots to trace gas temperature and density in physical processes. And actually, one of the reasons I'm here this week is Zita and I are working together with a collaborator in California, not to try and make maps like this with gases, but to try and do that with the solids. And that's a pretty big thing, and it's our collaborator in the US that came up with the idea, and there's very few people in the world doing it at the moment, but we're all trying very hard to map what the solid looks like. But here we have a map. What we've got here, the green lines are emission from carbon sulfide, CS, and inside what you've got is different materials from, I believe the white lines are where the dust is, and here are the different objects, but what you can see is here at the sides there's CH3CN, okay, oh that's the white contour CH3CN, what are the red contours then? Dotted contours, the one, this is the continuum, this is where the object is, my apologies, this is where the object is, and the white contours is where CH3CN is, that's the molecule we think is made on the surface of the grains, so as everything is warming up, we think it's desorbing, and so we don't see the CH3CN where the object is coldest or where it's densest. We actually see it slightly offset where the material is getting warmer. So we can start to look at how temperature is affecting where the gases are seen. Okay, final thing we can do is we can also try and link chemistry together by looking at what we call parent and daughter molecules. A lot of people do this in cometary studies, but we can do something similar. We can map an object in HCN, and then if we have HCN in the gas phase, and then we can actually photolyze it so it can go back to a CN molecule plus an H molecule, we can have a look at where that happens and where there's photolysis going on and the cloud is no longer shielded, we see the CN radical predominating, and where it isn't, we see it hydrogenated to HCN. And you can pretty much see that if we were to overlap these two things together, the height of the HCN is right in the middle of here where there's a gap in the CN itself. So we can start to look at the overlap and interaction between where molecules are being formed one from another and look at correlations to understand the chemistry. So how does chemistry actually happen? There's two key processes that we want to look at, thermodynamics and kinetics. And at this point everyone goes, oh. Okay, but actually it's really fundamentally important. If you think about one without the other, okay, it really doesn't work. Now the best way I can describe this is the way I describe it to 14-year-olds when I go into schools. Okay, so I know that you were all 14 once, so project your mind back to when you were there. And remember what it was like when you really liked somebody who sat in your class on the other side, okay? And thermodynamics is all about, if you wanted to go out with a boy or a girl on the other side of the classroom, you had to be brave enough to go and ask them out. It didn't matter whether you were a girl or a guy, you had to be brave enough to go and ask them, will you go to cinema with me tonight, right? They were never going to ask you, there's a barrier to overcome, right? You've got to be brave enough. It's the same for molecules, right? In order to form a molecule, the two atoms have to overcome a barrier, and then they get into a nicer energy state, a lower energy state if you like, a more stable state in a couple or whatever you want to call it, and they end up together, okay? But there's something else that happens as well. And imagine that you and your best friend, and this is the point where all the teenagers start laughing when I say this, because they're all nudging each other, because they're all, the person at the front of the room talks about boyfriends, but then they're all nudging each other because they'll think it's really funny that I realise that when you're 14, everyone fancies the same person at school. Now, I was 14 and you know that happens, so never mind, but they don't realise that. But just imagine, because generally there's always one person, one boy and one girl in the class, give or take, that everybody wants to go out with. And the bottom line is, it's not just about who they like when you're 14, it's actually, you have to be 14 to do this, but it's actually about who asks first. So it's not just about overcoming the barrier to asking, but it's also that you've got to be quicker than everyone else at asking. Because if you don't ask before your best friend asks, then you know, your best friend will get to go out with this guy rather than you. And that's exactly the same for the molecules. There can be many, many ways in which we can form, say, a CO2 molecule. But whichever pathway, first of all, we can overcome the barrier to, and also whichever pathway goes fastest, will be the way in which that process occurs in space. And so we have to think about kinetics and thermodynamics, and that's the best way I can find of describing it, okay? We need enough energy and we need enough time to form the products. And in space we have millions of years, so everything can always happen, but there'll always be a preferential pathway. And this is the proper way of really showing this. So we have reactants and products with some kind of energy barrier, and at the temperatures we have in interstellar space, 10 to 200 Kelvin, we really need no barrier chemistry. That means ion molecule reactions in the gas phase, or radical reactions. In reality, the molecular density is so low that three-body reactions can't happen. Generally, for an ion molecule reaction or any kind of two-body reaction to really be effective, we need a third body present to carry the energy away from the reaction center. So we can't add three things together and get a nice big molecule. We've got to do it one by one and use the third body to carry the energy away. But we don't have that option in the gas phase in space. And so what's really amazing though is despite that, here are all the molecules that we've detected in space. That's a huge number. I think this even doesn't have quite all of them on there now, it's something like 210. But I want to point some things out. Once you get from here, the 5 molecules pretty much upwards, look at what everything is. It's all long carbon chains. It's all long molecules with huge dipole moments. Why is that? Because a long linear molecule with a large dipole moment is very easy to spot in the radio frequency, because the large dipole moment means that it has a very intense rotational spectrum. Okay? It means that the rotational transitions are strong. It doesn't mean there's lots of that molecule in space. Okay? But take, for example, C6H6. It's certainly not on there because we haven't really detected a benzene ring in space yet. Okay? Now, no one's going to tell me that there isn't a benzene ring somewhere in space, right? And we know because we have these molecules, we call them PAHs, polyaromatic hydrocarbons. They're the carcinogenic black soot that comes out the back end of a car, to be perfectly frank, and an aeroplane and everything else, when we do incomplete burning of almost anything that's a hydrocarbon fuel. Now, we have smoking chimneys up in space that are pretty much dominated by, in carbon stars, by an environment which has carbon and oxygen and hydrogen in it. We know that we form dust, we know that we see in meteorites polyaromatic hydrocarbons. We have even emission features that we think are related to aromatic hydrocarbon rings in space. Now, indeed, we haven't said, oh, there's naphthalene or benzene or some other kind of specific PAH in space yet, and we probably never will, because all of them have very similar features. But on the other hand, they're very difficult to spot, because what we're looking at is really, we're looking at what we as chemists would call functional group transitions, stretching vibrations or wagging vibrations of the rings. We can't go and look at a rotational spectrum very easily, because the rotational spectrum of a molecule like benzene is in most senses, it's a very weak spectrum. And so it's very hard to see these ring molecules or cage molecules. They're very hard to detect. So we need a very huge column, so we need a lot more of that stuff, even to get a small detection on our radio frequency transitions. And not all molecules are rotationally active. Things like N2, which is predominantly missing from here. I'm in Stockholm, so I can mention O2. Yeah? I mean, Odin was quite successful at putting a limit on the O2 level. I mean, NASA spent, or Harvard spent a lot of money on SWOS, and certainly didn't find any O2 at all, not even in the remotest sense. At least Odin has been a little more successful in proving that there's a lot less O2 around than we thought was there. Now O2, we were trying to look at O2 by a magnetic quadrupole transition which occurs in the far infrared part of the spectrum. That is not the most easiest transition to go and look at. I know, I did my PhD in those kind of regions of the spectrum. Different molecules, it's not about always how easy is it to see if the molecule is present. It's about how easy is it for us to detect it. And there I come back to the problem of, imagine you're only walking around Stockholm, and therefore you're going to tell me what the Earth was like from just walking around Stockholm. If you really didn't have a television and you went back a few centuries and you really asked people, let's go maybe 1,000, okay, maybe at least people from Stockholm have been to my country and been raping and pillaging and wearing their horny hats, Maybe they've been as far as Greenland, maybe they've been to Lapland, maybe a bit into Russia. But they certainly didn't know Africa existed. They hadn't seen the Sahara Desert, I shouldn't think. They probably hadn't seen tropical rainforests. And so if you were to try and build a picture of the Earth just by only living in Stockholm and never going anywhere else, you would have a very incorrect picture. Yeah? And so what we have to be very aware of and very careful of, whilst we're thinking of all this chemistry and astrochemistry and astronomy and leading to biology, is being very careful not to stamp down somebody who comes up with a good idea just because there isn't a molecule on this list. Because the reality is this is what we're able to see by using the electromagnetic spectrum. We're limited by what nature gives us. Things like C60 are pretty much infrared inactive molecules. They have 1 or 2 modes. Okay? Things like benzene are pretty much infrared inactive. They're pretty much radio inactive. N2, the only place we see N2 is pretty much in the UV spectrum. O2, pretty much one transition in the far infrared. But it doesn't mean to say those things aren't necessarily there, and maybe they're not the most abundant form of that particular species, but we have to be very careful. Okay, religion aside, these are the molecules. I point out this one up here, especially to cosmologists, for which we cannot effectively explain how they are formed through these gas phase ion molecular processes alone. This is why we need to think about the dust. This 1% by mass of material that's sitting around in our baryonic universe, okay, in the universe we can really see and detect and understand, is playing a vital role in generating the H2. In fact, it's a very big problem because obviously the first stars must have had some H2 at some point to help them form, and we didn't have dust at that point because we hadn't had stars before, and so the question is, how did the H2 form? And there are a bunch of people, especially Alex Delgado, who is now retired but still works on it extensively, and what we think is that we think it's the light hydrides, things like beryllium hydride, lithium hydride, boron hydride, maybe even CH, that kind of thing that starts to form small dust clusters, which is probably potentially where H2 formation in very early stars might be a key process. But in the kind of stars we're interested in, H2 formation we now know occurs very effectively on grains. We understand the formation rate, and there are lots of interesting experiments going on around the world to understand the intricacies of the H2 formation. One of which is, for some of you who might be aware, H2 has 2 states, an ortho state and a para state. And what's very interesting is we don't always see the same ratio between ortho and para hydrogen as you would in thermodynamic equilibrium, which is normally 3 to 1. But actually sometimes we see almost a 1-to-1 ratio. And what's very interesting is if you start looking at how the process occurs on graphitic surfaces, for example, there is a preference for producing para hydrogen over ortho hydrogen. And this is actually of very great interest and use to people like Toyota, who are interested in how hydrogen can be stored and how it can be recombined. And so hydrogen formation seems very interesting to astronomers, but in our apparent hydrogen economy we're going to have, not that we need it, when I was listening to CNN this morning, because now the British are digging up all of the Libyan desert to allow BT to get oil out of it. Tony Blair was shaking hands with Colonel Gaddafi. That's clearly his next legacy to leave behind. Well, nonetheless, in our hydrogen economy, we should actually look at a lot of interesting ways in which we can form and store and recombine hydrogen. So actually a lot of the things we do for a space-based interest actually have a lot of other implications, and so we can be very excited in what we're doing. But there are a couple of other molecules here, CO2, H2O, methanol, CH4, I'll leave these 2 more exotic things out. They also don't form in the gas phase, they form in the solid phase, and they're the molecules we're really interested in. And this is the kind of process that's going on to form molecules in space. So we have some kind of carbon or silicate core, and it's surrounded by my ice layer. The ice is dominated by H2O, that is the predominant thing. The water ice is formed on the grain surface through reactions of oxygen and hydrogen, or OH and hydrogen, or H2 and oxygen. It leaves a little bit open-ended. I'm actually going to Paris next week to work on some experiments to do with that. And then CO. CO is the one unique molecule that really freezes out from the gas phase. It forms in the gas phase and then condenses onto the surfaces of the grains. But we form all sorts of molecules, NH3, CO2, all the kind of molecules we might expect to see in a very simple sort of chemical factory. And these are nice things. They're about 10 to 100 nanometers. So here we have our astrobiological nano factory, and if you can't get money for that, I don't know what you can get money for these days. So there we go. Other nice thing is these carbonaceous or silicate cores. They're nanomaterials, they're porous, they're catalytic, they have different pore sizes, so we're very interested in therefore looking at unique materials that people could be interested in from a production point of view. In fact, zeolites are quite good catalysts and mopping up agents, and these things are not a million miles away. Zeolites form under pressure, so they're not quite zeolites, but they're seeded probably with ions and all sorts of other things, so these materials are very interesting. And we have a weak hydrogen bonding network, and hydrogen bonding is a fascinating thing because hydrogen bonding is fundamentally important in the behaviour of water. If it wasn't hydrogen bonding, the water on this planet would not be in a liquid form predominantly, and consequently we wouldn't have the same kind of life and environment and everything else that we now have. And we think that probably water in a liquid form is one of the most important things for life. It's 70% of our bodies. It's pretty important for maintaining a pH balance in various different environments, whatever kind of animal you are. And it's the hydrogen bonding in water that really governs and controls a lot of its properties, how it's able to solvate ions and many other things. So the interesting thing for me in working in condensed materials, which happen to be very amorphous and porous, and useful understanding of hydrogen bonding, is that here I have another link to something else that's interesting in science, the hydrogen bonding community that's interested in models of liquid water and understanding the properties of water. And that's very important. It might seem a million miles away from understanding how a star forms, but in actual fact, fundamentally what we do now know is that the physical behaviour, the hydrogen bonding, the porosity, the structure of the water ice on these grains is fundamental to how all these other materials can be formed, how they can be condensed on the surface, how they can be released from the surface, how they're diffusing, what kind of environment we have available to do surface chemistry. So in actual fact it transpires that understanding hydrogen bonding is pretty fundamental to understanding the interplay between gas and dust in interstellar space, which is quite a big leap from atomic scale upwards. Okay. We can have chemistry going on at the grain surface itself, so on a bare grain, so that's pretty interesting. We can have chemistry going on the ice surface itself. And we can have chemistry going on inside the ice, driven usually by UV photons perhaps, but more likely by electrons, which arise from cosmic rays and secondary electrons. Potentially also we have the idea that the chemistry could be driven by X-rays, especially at the edges of disks near young stellar objects. But this is not really an area anyone's investigated yet, and I think we have so much to do that might be for the next generation to attack rather than me. Okay. So the key to large molecule formation basically is ice and dust, which is pretty nice because if we want to go to an astrobiological sense and we want to go to bigger and bigger molecules, then we need to think about ice and dust. I'm just going to skip this bit. And so one of the things I've been saying about is one of the things that I do, which is surface science. So surface science really paints a picture of gas-green-grain interactions on an atomic level. And I don't really want to talk about these processes today. I always have more than I need. But I want to sort of show you how solid-state astrochemistry and looking in astronomy really sort of collates together. So in this astronomy, let's look at the timescales first of all. So in that pre-stellar phase, that sort of black hole on the sky phase, we have around 10 to the 7 years where the molecules and atoms and so on sit around there. So it's quite a long time. We then have around another 10 to the 7 years for the actual star formation, the collapse phase to happen, and around another 10 to the 6 to 10 to the 7 years for planet formation. So some order of 10 to the 7 years and we can form a solar system. Typically in the lab, an experiment takes 12 to 48 hours, and I'm sure if I wrote to my funding body and suggested I wanted to do an experiment over a few times 10 to the 7 years, they certainly wouldn't fund me for that long, and I certainly wouldn't be around for that long to actually see if the experiment worked or not. So obviously we have a small timescale problem between the lab and space, but we have ways of overcoming that by modelling, by understanding, and that's why we need to get understanding at an atomic and molecular level, so that we can actually then scale up processes and change things between what's happening in the lab and what's happening in space. In astronomy, the grains are very small, the pressure is very low, and the temperatures are also very low. Getting these temperatures and pressures is really not that hard in the lab. We can do that. And we can even get the residual vacuum to be dominated by H2 gas by using certain kinds of pumps and everything else. And we can get the temperatures down by using cryogenic techniques. One of the problems at the moment is it's pretty hard in the lab to isolate a small grain and leave it just hanging in the middle of a vacuum and then do a bunch of chemistry on it and have enough signal to first of all see what's happening, but second of all have done everything on one single grain. You can potentially put your grains in a trap, but then you're in an environment with a magnetic or an electric field, which may be true because really space is just a very weakly ionized plasma of dust and gas, so maybe that's true. But of course, magnetic fields and electric fields can affect chemistry, and if we want to start understanding chemistry, view is generally you start at the bottom and build up. You don't start with the most complicated thing and see what mesh you get out and see if you can make it fit to something else because you've got too big a parameter space. So some people are trying now to work with traps, even ultrasonic traps, which is a very smart method of doing it because then you're not using electric or magnetic field, but it's still pretty difficult to trap materials. So today we use flat surfaces, although what we're starting to do is move towards using nano-templated surfaces. I'm working together with a group at Chalmers. They have a European nanofabrication centre over there, and they can actually fabricate surfaces very specifically, so we can start to understand how that's working. On the other hand, we also have a problem of flux and time, so we can look at chemistry that's driven by Lyman alpha or Lyman Werner UV band photons, but typically we have one of these colliding with a grain every 10 to the 6 years or so not very often. Most of the chemistry isn't UV driven. We can do that, but it takes about 5 seconds of irradiation in the lab to reproduce the whole lifetime in the ISN. And if we use a laser, we pretty much blast it quicker. Although, what we can do is we can still try and understand wavelength dependence on what's happening in those respects. We can have atom-molecule collisions. That occurs every 10 to the 4 years. This is probably what's driving most of the chemistry in dark clouds. We can dose around 10 to the 15 molecules per square centimetre per second. That's pretty controllable for us. We could go down by a couple of orders of magnitude there, but pretty much we're many orders of magnitude higher than the fluxes in space. But if we can understand that we're doing one molecule at a time chemistry, we can solve that problem. And X-rays and cosmic rays have a direct hit every 10 to 5 years. I don't really work on this, but people are now working on doing electron and X-ray induced chemistry, and you can do that. I want to skip over this. Okay, so that's it. So I'll just give another couple of minutes. So how do we go from molecules to life? Okay, so I've tried to talk a little bit today about what do we really know and what don't we know. What is chemistry really doing for us in space? And here we come to perhaps the part which is slightly more tenuous, because I'm always looking at a part where we can observe the molecules in space, where we can't get there, and where we can talk about the chemistry. Now, all the way at the other end, there are people who have, taken probes and visited, if you like, the surface of Mars, or observed the surface of Mars, visited environments like Titan with Huygens probe, had a look with the Cassini probe, are contemplating being on Venus Express or Mars Express, or in various different missions that are going to go to our local solar system. And you may ask, what is the point of going into the local solar system to look for life? Well, actually it's very important, because if our picture and our understanding of that star formation process are correct, what we're really saying is, from the atoms that we start with and the very simple molecules that we start with, the materials that are eventually leading to the formation of planets are the materials that contain all the ingredients that are necessary for life. Okay? It's the same as when you walk down to the supermarket, potentially on the shelf are all the ingredients necessary to bake a cake from scratch. Okay? Now you can go to the supermarket and buy a cake already made, okay, but if you want a sense of satisfaction, I guess you buy all the ingredients. Now if we never ever had ready-made cakes in the supermarket, like we did a few years ago, you'd always have to buy the raw ingredients, but eventually you could have a cake. Yeah, you just have to know the right recipe to go through with it. And in a way, my opinion is that it's a bit the same for life. Yeah? In the interstellar medium, in the protostellar disk, in the regions where we're forming stars and planets, we have all the ingredients, we have all the parts of the recipe that are necessary for the formation of life. We potentially have all the atoms there, we have everything in some kind of format. We don't necessarily have life there, we don't have little green men sitting on our astro-nano bioparticles, okay, ready to jump out as soon as there's a planet and start building, multi-story blocks of flats or anything else. But what we do have is we have the materials which, if they are delivered or get incorporated into a planetary system, could then, through many, many stages of further processing in the planetary system, end up being the potential for forming life. Because we know that our planet has undergone many stages of processing, bombardment. It's certainly not in the same state it was in when it was even first formed. We've had geological processing going on, we've had volcanic processing going on, weathering processing. It's certainly not even in the same stage. It hasn't happened the same to all of the planets, because we don't have 4 rocky planets that all look or have the same kind of starting point as Earth that just happened because of their distance from the sun to end up different. Fundamentally, they started off with kind of different mixtures, we think. Yeah? I mean, the gas giants is a little bit different. Potentially they've got a rocky and icy core at the centre, and they've got some hydrogen and helium around them. But even there we have a problem. Yeah? If we were to go back and reclassify Jupiter, we could potentially reclassify it now as a failed star, as a brown dwarf. It's giving out more energy than it's taking in. It's pretty much all hydrogen and helium. It hasn't switched on. It's not burning. Maybe it's the partner to our binary star system that never ever formed. Who knows? But one of the problems we have is that we don't really have the direct link. We don't know about the direct link between interstellar space and life on the planet here that we have. This is speculation. And so what a lot of astrobiology is doing is starting from the prebiotic Earth, from the early Earth, from other environments, and working backwards. And what I'm doing is I'm starting at the other end and working forwards. Well, maybe they're working forwards and I'm working backwards, I don't know, but we're working in opposite directions, hopefully to the same end. And the same end is to establish what the link is. And we already know that when the atoms in space are there as a recipe, we can use them to form these stellar nurseries and these molecular environments from which we form stars and planets. And we know that once we have a planet, we can potentially form life, but not always, because there aren't lots of little green men running around from Mercury popping across to Earth and saying hi to us. Okay, so that's kind of quite complicated. So here I have a kind of biological periodic table, fitting with the trend, and this one is coloured according to the importance of the species. So hydrogen, carbon, nitrogen, oxygen, they're in yellow, they're very important. The red ones are the next most important, and then I think it must be the green ones. And so we go on and down and down and down. But what you see, okay, is what's kind of quite interesting. What I like about this, hydrogen, carbon, nitrogen, oxygen, at least those 4 were at least on my astronomical periodic table, right? They appeared, they were there. That was very important. The trouble is that even when I go to the next level, potassium, calcium, sodium, phosphorus, chlorine, all of those were missing. Right? So already biology is a minority thing as far as space is concerned. Because it's not using the major constituents of space, it's using a lot of the minority constituents of space. It's exceptional, it's not normal, it requires certain things to be in certain high concentrations, which isn't, a lot of people start with a solar abundance of atoms and try and work out what's going on in the world. Well, great. But unfortunately, the solar abundance thing doesn't really work when it comes to explaining biology, because that's not the way biology's evolved. Yeah, helium, that's like pretty, almost not very relevant at all. In here we go. These are all the least relevant. No, well, purple things are the least relevant, and then the brown. The blue ones, things that, gold is not a fundamental thing to your body functioning, thankfully, and we all like it, we'd all like to be bought it, but it's not actually fundamental to your body working, whereas something like nickel or iron or manganese, these are much more, chromium, these are much more important in your body. Okay, and something like helium, okay, it's down there with all these noble gases and gold and silicon, and silicon, of course, is in all the silicates. There's plenty of silicon in space, there's plenty of helium in space, but neither are particularly relevant in our biological processing. So, in a general sense, space is not the most useful environment in which to develop life, actually. In the same way as it's not for chemistry, and so we have to bear that in mind. Okay, this is my not biologist's view of how we can get from simple molecules to life, and please excuse the huge jumps that are made if you're a biologist in the room. We can go from simple molecules, and if we have simple molecules, we know as chemists that we can make complex molecules and polymers. And what I mean by that is we know that we can go from simple molecules in synthetic organic chemistry to very, very complicated drugs. We know that we can build things up like RNA sequences, DNA sequences, and all these other things. We know an awful lot of chemistry and molecular understanding. We know we can do a lot of different things with molecules. We can be very exotic, we can be very smart if we're trained in those things. On the other hand, we can also make materials that can make lipid-like cell membranes, that can make encapsulations of molecules. We know how to do those kinds of things. So we have all the tools at our discretion on the lab bench here on Earth to think about ways in which we could make pretend cells or real cells, the ways in which we can make simple proteins, enzymes, molecules that can lock into protein and enzymes. That's what there's a whole host of life sciences, very smart people doing a lot of time, yeah? Taking simple molecules, making a more complicated molecule, adding complicated molecules together under certain specific conditions, and getting to very complicated processes. So we know it can happen. So I want to make a little jump, really, that we can go somehow from simple molecules to complex molecules and polymers to the two key things that I think are really key to life. On the one hand, we know that somewhere along the line we've got to get to this RNA, DNA type world. On the other hand, we've probably got to have a cell to contain the chemical processing that's going on. A piece of RNA or DNA, well, RNA is not stable, a piece of DNA on the bench sitting there is not going to suddenly spontaneously form a mouse, right? There's an issue that we have to think about, having some kind of environment where the pH can be controlled, where the ion flow can be controlled. It's another little nano factory, if you like, our cells, where the biology can really go on. And I'm not a biologist, but I have the feeling those two things are the key things. So if we want to search for it, I think in many ways this is the thing that we have the potential to be able to form and look at in interstellar space. And the reason I say that is because there's a very nice experiment. It was published in Nature, and it was all about forming amino acids in ices. But actually, the part of the experiment they didn't really blow up and talk about that much was the part of the experiment where they found the amino acids and looked at them and said, oh look, we made an amino acid, because actually making an amino acid is quite easy. I mean, Urey Miller did it very effectively in the 1950s with a bit of lightning and some ammonia and water and a little bit of a mess in a tube. And if you do that, if you want to go and ask the chemist for a big gas tube, put some water in it, some ammonia, some nitrogen, some methane or something, and put a few discharges through it and sample the gas afterwards, and you can make amino acids too. It's pretty easy to do, right? So making amino acids isn't the hard thing. Keeping them there and not destroying them again is more difficult. And actually making cells and cell membranes is much more difficult. Making something that is not even a proper cell membrane, but even just that's a lipid-like structure, which is going to have a hydrophobic end and a hydrophilic end. And what's very interesting is in this whole process of making these amino acids and blah, 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 if you take the material that's left behind and you solvate it in a liquid, what you find is that there's whole bunches of molecules in there which start aligning into micelle type arrangements. They have an end which is hydrophobic and an end which is hydrophilic, and they'll actually start sort of aggregating like solvents with all their heads and tails and sitting around with something sitting in the middle, like normally a few water molecules or something. And I think that's much more interesting, because here we start to isolate. They're not really cells as such, but here we start to isolate when we melt the interstellar ice, if you like, or when we start aggregating ices together to form a cometary species, and that crashes into the early Earth. Here we have a way of delivering something that, without any more chemistry, has already got to a point of having something in it which has a cell-like structure. It's not a cell. I know it's not a cell. Please don't quote me on that, because it's biology as a cell is much more complicated. But at least it's a structure which has some kind of micelle structure and has some kind of environment around it. And I think that's much more exciting. I think that's something which we should pursue much more. Okay. I think it's more than time enough that I stopped. I'd like to thank you all very much for your questions, and for all of you have had just the most fascinating faces. So I hope you've not just painted them on, and I hope you have actually enjoyed what I've said and you've learned something new. I love this little cartoon, because I think it summarises exactly what we do, that whether you're looking on the large scale or the small scale, things are really very much the same, and it's all the same chemistry and physics that really helps us to understand the origins of life. Thank you very much.
Thanks very much. Other questions?
Yeah.
You had this picture where you showed the accretion, the protostellar disk, or star forming region, where you showed the outflows in this cone-like shape. But there was also inflow. And did you say it was a different object, or was it the same object?
It's the same object.
Yeah.
So.
And so it was in the perpendicular direction then?
Yeah. So
right.
so the outflow is kind of like this.
Sure.
And then the inflow
Yes. So what's the velocity, the relative velocity difference?
Not a clue, but I can look it up afterwards for you.
Because it should perhaps be many orders of magnitude.
Many orders of magnitude, yes.
Yeah.
It is many. The jets are moving very fast and the inflows are moving very slowly.
Yeah.
Yeah.
Any other questions?
Yeah,
Yes?
right.
So, I mean, the structure of the grains,
Yes.
how well determined is that? It seems to me rather speculative. I mean, you have a core and you have something outside. I mean, it doesn't come here to Earth. You can really...
No, right, okay. Well, one of the things... Oh, I don't know if I have it. I skipped over it.
Yeah, I think you had it there.
I'm just looking for the specific...
There.
Yeah, okay. Let me just... This is the quickest way. Oh, well, maybe not. It will crash. I have a picture that will help. Of course, it's probably the picture before this, I think. Yes. Okay, so this is a picture of an interplanetary dust particle here. This is made of silicon dioxide. Well, it's probably olivine or pyroxene, so it has magnesium and iron in it as well. And this is actually a picture which is taken with a transmission electron microscope, and it's really a small inclusion that was inside of a meteorite which fell to Earth and then was looked at, and this was an inclusion in it. Now, what they can do is, from the gases that are trapped and from the isotopic ratios, they can tell if material is material that's from the pristine protostellar disk from which our planet's formed, or whether it's processed material. And mostly meteoritic material is processed material, because it's material that sat in the disk for 10 to 7 or 10 to 8 years whilst the planets have been forming, and therefore it's undergone a lot of subsequent processing. But inside you sometimes find material like this, which is more pristine material. And immediately what you see is that it's fractal. It's only, I don't have a scale on here, but it's only about 100 nanometers across, and it's fractal and it's very small. So what it's really made of is small clusters of silicon dioxide that are stuck together. And in some places it looks a bit more melted together, in other places it really just doesn't. Now, I think that the great thing about this is, just if you were to look at sooty particles that come out of a candle flame, it's pretty much the same thing. The particles are aggregated together, and they're a big mess as far as how fractal they are, and they're not nice spheres or anything else. And almost certainly this is what the dust really would look like if we could go to space and get some. But as the nearest star forming region is a few hundred light years away, then that's not going to happen. So what we do is we infer from the material that's falling into our solar system, it's called interplanetary dust, like this, we infer what the material is like in space, and from the spectroscopy. Now, astronomers, when they model it, of course, model nice spherical particles. I tried with my little picture to draw it not spherical, at least. And in actual fact, as a chemist, this is brilliant for us, because here's a really rough, horrible surface which we can put all sorts of things on. And we have done some work. I'm actually going to talk about that a little bit on Friday, I think, not this afternoon, or maybe this afternoon, we have some ideas where we seem to have seen features in observations which refer to CO actually bound directly to this grain surface. So, as a surface scientist, if you bind CO, if you use CO to probe a surface, you can see chemisorphed and physisorphed states, and you can start to understand the structure of a surface. That's exactly what you do as a surface scientist. And there is a chance that we've seen that kind of thing in space, but obviously, again, we're back to the same problem with the benzene. It's really hard to see that unless we have a strong transition and all those other problems. So it is speculative, but my feeling is when you speculate and all the pieces of the jigsaw start to fit together, it makes a lot more sense. So you don't take any one piece of information in isolation. That's my approach. But we could be wrong. That's the good thing, right? You can speculate in this field.
Another question.
So who is Jim in your title?
Ah, you're not a Star Trek fan.
Sorry about that.
So there is this always this live Jim, but not as we know it, that Dr. Spock says. So yes, normally when I speak to school kids, they ask me that because they don't really remember that part of Star Trek. It's all Voyager or Deep Space Nine or something. So, yeah, that's the geeky part.
So is there actually in nowadays astrobiology, is there a lot of science going on with cell membranes, or is it just something that you really...
Absolutely. No, I mean, no, there is... people who do astrobiology are there all the way from people who are studying hydrothermal vents and the kind of chemistry that occurs there. We have sulfur-based bacteria in hydrothermal vents. They're actually not carbon-based at all, but sulfur-based, We have extremophiles that live in strange environments, like in the Antarctic or in the middle of deserts where we thought there was no life, and if we look on a microbial sense. And they're the kind of things that people tend to study because they're more likely the things that we might expect to find in subsurface oceans in Europa or on Mars or whatever. And that's what a lot of people do. Other people call astrobiology the search for extrasolar planets. Other people call it search for big molecules in space. I mean, tenuously speaking, we have astrophysics because we can see physics of astronomy, and we have astrochemistry because we can see the chemistry of astronomy, but we don't actually yet have astrobiology because we don't actually have any biology that's extraterrestrial to study. So it's a bit of a anomalous word that we've acquired and we use. So in the UK, we have this very strong anti-astrobiology kind of mission, and people try not to use the word, but as everyone uses it everywhere else in the world, especially NASA, then you have to use it. You have astrobiology here in Sweden, right? It exists. I exist in the UK, but we just try not to use it. It annoys the biologists, it annoys the chemists, and only the astronomers are happy with it, so you have to be careful.
Any other questions? Okay.
So thank you all very much indeed for coming and listening. Thank you.